Good morning. So yes, we are starting a new unit today, but hopefully it won't feel like a new unit for a while. It might feel like a little bit of review, or just nothing too rigorous for a bit. So the first thing I want you to do is take a minute, notice and wonder with these three tables, and seriously pause the video and make sure you're trying to see what's going on in these tables. There's a pattern in each one of these tables. One of them's fairly obvious, one of them's pretty obvious, and one of them's a little bit trickier. So take a moment, pause the video. What do you notice about each table? What kind of patterns of growth or decay do you see? So like I said, the first one is pretty easy to see. I looked at this one and I saw, 0 to 5, 5 to 10, 10 to 15, 15 to 20. I'm adding 5 each time, which makes this table a linear relationship, or linear growth. That equation would be y equals 5x minus 5. Doesn't matter if you got that or not. This is the important part, linear growth. Whereas this one right here reminds us of our previous unit because every time x goes up by 1, my y is doubling. So my equation here would be y equals just, let's see, we're doubling, so it's 2 to the x. I guess it'd be 1.5 times 2 to the x, because this is exponential growth. And again, if you don't get the formula, that doesn't really matter. The point is noticing is exponential change. So then, we look at our last one. If I look at that one, or the first one, I guess. The first one I see are 8 to 11. That goes up 3. Then I go down 1, down 5, and down 9. So I don't really know if I see the whole thing. It goes up and then it goes down. So it's a little bit weird. But I promise you there is a pattern here. So try to take a few seconds, pause the video, and see if you can figure out if you notice a pattern here. All right? Oh, geez, sorry. So, the pattern isn't really in these numbers. The pattern you can see more of in these numbers. Because if I go from 3 to -1 to -5 to -9, that is a linear pattern. So really what happened here is I'm going up by 4 less each time. The amount of my growth is decreasing by 4. Then I went down 9, minus 4 more. And so next time I would go down by how many I would go down by how many? 1, 5, 9. I go down by 13, so I'd be at -17 here. Because again, every time I go down by 4 more than I did the previous time. All right, and if I were to find that previous number up here, let's see, 4 more than that, I have to add 7. So my first one at 0 would be 15. And again, all that matters here is that you sort of see this part here. This is like the goal here, to see that we're decreasing by 4 more each time. And again, we're going to talk more about this and what it actually means later, but the goal is seeing that there's a third type of growth we haven't quite talked about yet, and we don't have a word for it yet. It's kind of weird, but we'll see what it looks like in a graph. We'll see what kind of situations it could model, but it's a different type of growth / decay, and really our whole rest of the year is going to be focused on looking at stuff related to this type of growth, because it's a little bit different. All right. Okay, so we're going to look at an application. This is the only application we're going to do today, actually. We're going to keep these lessons really bite-sized, hopefully, just one little thing at a time. All right, because that's really the best way to learn brand new material from home, is keeping things simple. So Noah has 50 meters of fencing to completely enclose a rectangular garden in the backyard. All right, so draw some possible diagrams of Noah's garden. Label the length and width of each rectangle. So let's keep our minds open, because this is something you can all do. We have rectangles, right? And we have 50 meters of fencing. So rectangles, they got length and they got width. Length's got to be the same on both sides. Width's got to be the length on both sides. So I know my perimeter got to be 50. And let's be real, he's going to use all that fence. He wants a big garden. He's going to use 50 feet. Meters, sorry. That's a lot of meters of fencing, but he could use 50 meters of fencing. That would probably enclose my entire property. Anyway, 50 meters of fencing has to go into lengths and widths. So really, 50 meters of fencing has to be used for 2 lengths and 2 widths. So we have to figure out possible dimensions. I'll do the first one with you. So basically, I need 4 numbers. These two are the same, those two are the same, that add up to get me 50. So let's just say my width is like 10. If my width is 10, what does my length then have to be in order for me to use all of my fencing? Well, all right, so that's 20. And I'll do 50 minus 20 to see what's left. 30. So that 30 needs to split up into both of those areas. Gives us 15. All right, so 10, 15, 15, and 10. That adds to give us 50. So that's one possible combination I could do. Now I'll do a different combination in pink. What if I said I'm going to make my long side like 23? So if I make my length 23, here's a different strategy. Well, the whole thing has to be 50, right? 2L and 2W has to be 50. So I could divide that by 2 and say that length and my width have to equal 25. If I add them together, they have to each be 25 total. So if my length is 23, my width then has to be 2. Let's think about some constraints. Wow, Unit 1 flashback. Constraints. Length and width. Can it be negative? No. Length has to be greater than 0. And also, length maximum, let's think, if I have a length of 25, what's my width got to be? My width's got to be 0. And that doesn't quite make any sense. That's just a line of fencing. Doesn't really work. So length has to be less than 25. All right, same with my width. All right, so length and W have to be between 0 and 25. All right, so try to find a couple more combinations. We've got 1 combo and we've got 2 combos right here. Try to find more combinations. And then we're going to plot some values. We're going to plot length and area on the coordinate plane. All right, so we're going to do that after finding area of all these rectangles. So finish drawing your rectangles first. Try to draw a couple more, then we'll come back to this. Okay, so the next question asks us to think, find the length and width of such a rectangle that would produce the largest possible area. So they haven't talked about area yet today. So area, as you remember, is length times width. So let's go ahead and find the area of all these rectangles. We have 3 rectangles up here, kind of. We're gonna find their areas. So if area, to make a light knot, like a huge shadow. Better. So if area is length times width, then here area is 10 times 15, which is 150 square meters. Okay, and here, area is length times width. So area is 23 times 2, which is 46. That's a smaller area. Now listen over here, if this is a rectangle, the area would be 25 times 0, or just 0, which is kind of why this is not a rectangle, because it has no area. There's nothing between those side lengths. So, we notice which rectangle had the bigger area. This one, this one, this one. And that's because this one right here, 23 by 2, that has a long, skinny rectangle. And this one here is a shorter, more wide, more square-like rectangle. Notes are sloppy. Square-like is, you don't need to know that. I'm just gonna cross that off because it's so messy. Okay, so try to find the one that would produce the largest possible area. Pause it for like 2 seconds, see if you can brainstorm an idea, and I'll just show you. So we're gonna have the largest possible area when the length equals the width, so when they are the same. So, all right, so if length and width add 25, that would be when it's right half of them. So half of 25 equals 12.5. So if my length is 12.5 and my width is 12.5, my area would be 12.5 times 12.5, which is, oh my goodness, I have no idea. Let's see. Let's see, 144, 6, 6, and 0.25. Okay, so that's 156.25. By the way, we're going to learn how to multiply that by this or review this later in the unit because this is actually going to do a lot for our unit. Cool. So the area is 156.25, a little bit bigger than 150. So that was pretty close to the biggest, but this is really going to be our biggest. And if you try anything else, if you try like length equals 12.4 and width equals 12.6, you'll find that the area is a little bit smaller than that. So we're going to now try to plot some values for length and area. So if I plot my purple one, my length is 15. It's 15 is my length, and my area was 150. So let's see, 15, 150. Okay, and then I'll do my pink one, 23, comma 2. 23 is like here, and then 2. No, I'm sorry, not 23, 2. 23, and the area is 46. So 23 and 46 is like, here-ish. And then 25 and 0. We'll put that on there. So then 25 and 0. Okay, so we got our 3 points. Cool. We'll come back to that graph in a bit. So let's flip over. What do you notice about the plotted points? So think about what you do notice about the plotted points. Is there anything specific you notice about it? We'll come back to that question in a minute. So let's add some more points. The points 3, 6 and 22, 66 each represent length and area of the garden. So basically, they're saying that if a rectangle has a length of 3, the area is 66. And if the length is 22, the area is 66. Interesting. Think about why that is. And we're going to plot these 2 points on the plane. And what do these points mean in the situation? So think about that, and I'll go plot them. Three, 6, 66 is like pretty dang close to in between. 22, 66. This graph is insane. Okay, cool. All right, so what do they mean? Well, they mean that a rectangle with length 3 has area of 66. And the same thing with 22. A rectangle with length 22 has area 66. So that kind of makes sense, right? And that kind of comes down to our are you ready for more down here? What happens to the area when you interchange the length and the width? For example, if we took the one we drew as 15 and 10 and switched it, you would have a rectangle with a length of 10 and a width of 15. And I hope we are at the point where we can just accept the fact that they are the same rectangle but rotated. So the areas would be the same. So that can help us with our graph. Oops, just dropped something. So when my length was 15, my area was 150. So that ordered pair was 15, 150. But also, my length could have also been 10 here. So I could also have the point 10, 150. So I could do 10 and 150. And then for here, for the pink one, my length was 23, but also my length could have been 2 if I had turned that rectangle, 2, 46. So now I have 2, 46. So now I've got this graph that looks kind of like a trapezoid. Let's see. So let's try a couple more. Wait, is this? These should be much closer together. Whatever. Because that's a 2. So I'll put that like closer to the middle. That's a 3. I'll put that closer to the middle. I'm not getting quite the right shape here because these points are not plotted that well. Put that a little bit closer there. There we go. Okay. And you're like, shape? What do you mean shape? This graph looks like nothing. Well, we'll see. So let's find a couple more. We're going to do a couple more points. So let's plot more length and area pairs. So let's just do a couple. Let's just say the length is like, I don't know, we're missing a lot of points. We'll do like, let's do like 20, and we'll do like 17, and we'll do like some other numbers there. So I'll say my length is 20. I'll do a length of 17. These are not drawn to scale, as you know. You know me by now. I'm not drawn to scale. And we'll do a length of like, I don't know, let's just do like 8. No, I'm not gonna do 8. You'll see why. We'll do 9. All right, so find the width and the area if those are my lengths. So remember, from before, the length and width added up to get 25 because all the sides added to get you 50. So 20 and 5 got you 25, plus 20 and 5 got you 50. So it's 20 by 5, and then 17 by 8, that's why I didn't do it over here. 17 by 8 got us 25, and then got us 50. So then if I multiply my side lengths, 20 times 5 is 100. So my ordered pair would be 20 and 100. And then over here, 17 times 8, that area will be 136. And for my last one, if my length was 9, my width would then be 16. Again, clearly not drawn to scale. But the point of it is that if my length was 9, my width could be 16, my area would then be 144. And again, what if we interchanged the length and width? So flip-flop length and width. Then I could say, well, 20 100s is an ordered pair, but also 5 100. And also 8, 36 with 17 136. And 9 144 and 16 144. So we're seeing all the y values getting repeated twice. So let's see if I can remember. Okay, we had 5 100 and 20 100. That's an easy one. And then we had 17 and 8 136. So 17 136 and 8 136. And then we're not getting a great look at the shape of this graph right here. That's okay. and then 9, 144, and 16, 144. So let's see, we got 9, 144 is like pretty close to the top there. And then 16, 144. And let's remember, we also had this point here when our length and width were 12 and a half. And our area is 156.25. So we're just going to go ahead and I'm going to show you what this graph's general shape is. You might have seen it. It's a big curve. And this curve, turns out, does go down like a little bit steeper at the end. It's kind of flat at the top, then steeper at the end. Because remember, the length of 25, that area was 0. And the width of 0, that would also be 25. I'm sorry. If the length is 0, the area is 0. And if the length is 25, the area is also 0. Let's try one more, just so you really get the hang of it. So if I have a rectangle and my length is 1, what's my width? Well, that's 2. 48. 50 minus 2 is 48. Divided by 2 gets me 24. So 1 and 24. So my area is 1 times 24, which would be 24. So if I have an area of 1, I'd be right here. So I'm still seeing that same pattern. So length 24, area 1. No, I'm sorry, length 24, area 24. Be like right here. So there's my nice completed graph. And notice all those y values actually happened twice. And I do have that general curve there. So notice this type of relationship between length of a rectangle and the area of a rectangle is not linear. It's not a straight line. As length increases, the area goes up, but not at a constant rate. And it's also not even a growth factor. It's not exponential because the growth slows down and then stops. And we'll sort of see if we can figure out how we would define this growth in the coming lessons. But for now, we've done good with this, and that's all your practice problems. They cool down basically are based off of, so if that made sense, you should be in good shape.